So this is lab 3, black hole. This lab in both parts uses Newton's second law of universal gravitation, position and velocity update formula, and the parallel perpendicular forces to calculate the mass of a black hole. So basically what's happening in part 1 is that a star of known mass is orbiting a black hole. The forces between the star and black hole are calculated to find the mass of the black hole. The system is the black hole, the surroundings is a star, and this is what we get as results. Here are the fundamental physics principles and equations used in both part 1 and part 2. Here we have Newton's second law, which is just F net equals dp over dt. We have the universal gravitation equation. On number 3 and number 4, we have velocity update and position update formula. Number 5, we have that F net perpendicular equals the centripetal force. Then we have on number 6 that F net parallel equals the change in the magnitude of the momentum over time. And then we have that F net equals F net perpendicular plus F net parallel. Here we have the initial conditions where we have the gravitational constant, the known mass of the star, delta t, and then the time for the first observation data point. We are then calculating momentum initial and momentum final by doing mass times velocity, initial and final velocity. Then we are finding the change in velocity and the change in momentum. We're then using those values to calculate dp dt, which is just the change in momentum over delta t, and we denote this as F net. We are then trying to find the parallel component of force. So first we find p hat, which is just the direction, and that's just dp dt over the magnitude of dp dt. Then we find the magnitude of the force, which is the magnitude of p final minus the magnitude of p initial over delta t. We then multiply those values together to get the parallel component of force, and we denote this F net pair. And then to find the perpendicular component, we subtract F net minus F net pair to find dp dt perp. And then we use this information to find the mass of the black hole by setting the universal gravitation equation to mv squared over r, which is the centripetal force equation, and then manipulating that and to find the mass of the black hole, as you can see right here. So when we do this, we're going to get multiple values in glow script due to the changing position. But then I put them all in Excel and averaged them to get a mass of the black hole of 5.09 times 10 to the 13th kilograms. Let's just talk about what this means. So like, how are the net force and its components different from the rate of change of momentum in its components? So as you can see with this equation, both values are the same mathematically. With net force, however, values of multiple forces exerted on the system need to be known. However, with rate of change of momentum, we only need to know the change in motion of velocity, which makes it easier to use this value. Now part 2. The goal of this part is to use the mass of the black hole calculated in part 1 and to use that to determine an initial velocity of the spaceship to get close to the black hole and leave the system without crashing. So to do this, we find the net forces on the spaceship from both the black hole and the planet and use a simulation to determine an initial velocity through trial and error. Our system is the spaceship and our surroundings were the black hole and the planet. So these were the results right here. All right, so here are the initial conditions. We first have the mass of the black hole, which we found through the part 1. These are just the constants, like the gravitational constant, planet mass, ship mass, delta t, and the initial time. Then we have the maximum time interval. And then these are the initial conditions for the planet, where we found planet speed and planet velocity using the planet speed. And then these are the values of ship speed, x and y, found through trial and error. So in these two parts, we're using the gravitational, universal gravitational equation to find F net of the black hole and the ship on the planet. Then we are going to find the net force of the spaceship by also using the gravitational equation. And so then we just find F net on ship using the same process we did above. And then we update the planet velocity and the planet position using velocity and position update formulas. And then we do the same thing for the ship to simulate it in the model. Simulation, we got that the initial velocity could be this to meet the goals that we discussed previously. Errors for the experiment were that the velocities were found using trial and error, which means that there could have been room for human error, like the different velocities could have also worked to get closer. We also assumed what forces were acting on, like we simplified it a lot, and then there was a pretty short time interval which could have impacted the results. We had this what if question, and basically I was just unable to find this value in the simulation. However, I know that this value would need to be large enough to overcome the gravitational force of the black hole while still orbiting the object.